Picture this, a faint, wispy cloud hovering near the southern skies, so unassuming that ancient mariners once used it as a celestial guide. But the Small Magellanic Cloud is far more than a navigational landmark. It's a cosmic treasure chest, brimming with mysteries that defy explanation. Nestled just under 200,000 light-years away, this dwarf galaxy is a playground for the bizarre, a place where reality seems to twist at the edges. Astronomers have spent decades peering into its depths, only to stumble upon objects so strange they challenge everything we think we know about the universe. And today, we're diving into 30 of the most bewildering discoveries hidden within its starry folds. What makes the Small Magellanic Cloud so special? For starters, it's one of our closest galactic neighbors, a satellite galaxy orbiting the Milky Way. But unlike our home galaxy's ordered spirals, this place is chaotic, wild, a relic of the early universe where star formation runs rampant and the rules of physics sometimes seem to bend. Here, glowing nebulae pulse with unknown energies, rogue stars streak through the void at impossible speeds, and entire clusters of matter vanish without a trace. It's a realm where the ordinary becomes extraordinary, and the unexplained isn't just common, it's expected. Now, imagine uncovering objects so peculiar they shouldn't exist. Hypervelocity stars racing faster than any known force could propel them. Ghostly radio signals with no identifiable source. Dark, gaping voids where starlight simply disappears. Each one of these enigmas tells a story, a puzzle waiting to be solved. Some could redefine our understanding of dark matter. Others might hint at entirely new cosmic phenomena lurking just beyond the edge of human knowledge. And that's what makes this journey so thrilling. Because as we explore these 30 strange objects, we're not just cataloging curiosities, we're peering into the universe's deepest secrets, one mystery at a time. So, are you ready to step into the unknown? Let's begin. The first stop on our journey through the Small Magellanic Cloud's strangest objects is a site that seems ripped straight from a cosmic ghost story, NGC 346. This sprawling nebula, bathed in an otherworldly blue glow, is one of the most active star-forming regions in the galaxy, yet it behaves like nothing else we've seen. Most nebulae are stellar nurseries, yes, but NGC 346 is different. Its massive young stars, some dozens of times heavier than our Sun, should have blown away the surrounding gas clouds with their fierce radiation. Yet here, the nebula clings to them like a spectral hand refusing to let go. What makes this place even eerier, its structure? While most star-forming regions are chaotic tangles, NGC 346 has an almost sculpted quality, with delicate filaments of gas swirling in intricate patterns. Some astronomers compare it to a cosmic spiderweb, with newborn stars gleaming like dewdrops caught in the threads. But here's the real mystery: those filaments shouldn't be so organized. The intense stellar winds and radiation from the massive stars should have shredded them to chaos. So why haven't they? One theory suggests hidden magnetic fields are weaving the gas into these ghostly shapes, acting like invisible threads holding the nebula together. Another possibility: the Small Magellanic Cloud's lower metal content compared to our Milky Way creates a different kind of stellar feedback, allowing these structures to persist where they'd otherwise vanish. And then there's the glow. Most nebulae shine pink or red, the classic hue of ionized hydrogen. But NGC 346 radiates an eerie blue, a sign of intense ultraviolet light from its young, monstrous stars. It's so bright, it's visible even from Earth with a small telescope, a haunting beacon in the night. Yet for all its beauty, this nebula is a cosmic paradox, a place where stars are born in violence, yet the surrounding gas remains eerily serene. It's as if the universe itself can't decide whether this is a cradle or a graveyard. And that's what makes it our first unforgettable stop in this gallery of celestial oddities, because sometimes the most beautiful things in space are also the most inexplicable. Next on our tour of cosmic anomalies, we encounter a celestial fugitive, NGC 602, a young star cluster with a serious case of wanderlust. This sparkling group of newborn stars sits in the wing of the Small Magellanic Cloud, but here's the twist: it's nowhere near where it should be. Star clusters this young typically stay nestled deep within the gas clouds that birth them like chicks under a mother's wing. Yet NGC 602 has broken free, drifting through space as if pushed by some unseen force. What makes this runaway cluster so puzzling? Its age. At just 5 million years old, barely a cosmic blink. These stars haven't had time to slowly meander away on their own. Their current location suggests something dramatic kicked them loose, sending them careening through the galaxy at breakneck speed. One leading theory points to gravitational chaos, perhaps a close encounter with a massive object, like a rogue black hole or another dense cluster, slingshotting these stars into the void. Imagine a billiard ball striking a cluster, sending stars scattering like marbles across a table. But there's another, even wilder possibility. NGC 602 might be the survivor of a galactic crash. The Small Magellanic Cloud has a violent history with evidence of past collisions and near misses with its neighbors. Some astronomers speculate that an ancient clash with another dwarf galaxy could have sent shockwaves through the cloud, flinging entire star clusters like confetti. If true, NGC 602 isn't just a runaway, it's a refugee from a cosmic demolition derby millions of years in the making. And then there's the cluster's own stars, which add another layer of intrigue. Most are massive, blue and brilliant, the kind that burn fast and die young. Their intense radiation has carved a stunning bubble of glowing gas around them, like a cosmic snow globe shaken by stellar winds. But here's the real kicker: that bubble isn't symmetrical. It's warped, stretched in one direction as if the cluster is still moving, still fleeing from whatever sent it spinning into the void. So what really happened? Was it a gravitational kick, a galactic collision, or something else entirely? For now, NGC 602 keeps its secrets, a glittering mystery racing through the night. And that's what makes it so fascinating, because in the Small Magellanic Cloud, even the youngest stars have stories to tell, if only we could hear them. Now we turn our gaze toward two of the most perplexing residents of the Small Magellanic Cloud liner, X1 and X2, a pair of cosmic predators lurking in the shadows. These twin black hole candidates don't just defy expectations, they quietly rewrite the rules of what we thought we knew about these gravitational monsters. At first glance, they appear as faint smudges in X-ray telescopes, their emissions flickering like distant streetlights through fog. But peer closer and the strangeness unfolds. Most black holes fall into neat categories: stellar mass ones, born from collapsing stars, or supermassive behemoths anchoring galaxies. Liner X1 and X2 fit neither mold. Their X-ray signatures pulse with unusual rhythms, too erratic for typical stellar mass black holes, yet far too dim for supermassive ones. It's like hearing a heartbeat that speeds up and slows down at random, leaving astronomers scrambling for answers. Some suggest these objects are intermediate mass black holes, a rare and elusive class suspected to exist but rarely caught in the wild. If true, they could be the missing link in our understanding of how black holes grow from small to unimaginably large. But here's where it gets even weirder. Both objects emit what's known as low ionization nuclear emission line radiation, LINER for short, a type of energy usually associated with aging galaxies, not isolated black holes. This gas, typically stirred up by supermassive black holes at galactic centers, shouldn't be here in a dwarf galaxy with no sign of such a titan. So why is it? One compelling theory hints at a violent past. The Small Magellanic Cloud's chaotic structure suggests it may have cannibalized a smaller galaxy long ago. If true, Liner X1 and X2 could be the remnants of that ancient feast, the cores of two galaxies, now stripped down to their darkest hearts, orbiting one another in a silent dance. And then there's their proximity. These two objects are closer to each other than any known pair of black hole candidates in a galaxy this size. Are they gravitationally bound, destined to spiral together in a cataclysmic merger millions of years from now? Or are they mere cosmic neighbors, their apparent closeness just a trick of perspective? For now, they keep their secrets, their X-ray whispers too faint to decode fully. But one thing's certain: wherever they came from, whatever they are, Liner X1 and X2 are proof that even in a galaxy full of oddities, some mysteries stand apart, daring us to look deeper. Among the cosmic oddities scattered through the Small Magellanic Cloud, few sparkle as mysteriously as BPM 37093, a white dwarf star that's essentially a diamond the size of a planet. This celestial jewel isn't just a poetic metaphor. Its core is quite literally crystallized carbon, crushed under unimaginable pressure into a structure that would make any gemstone on Earth seem like dust. Imagine a diamond 10 billion trillion carats in size, floating in the void. That's BPM 37093. But here's what makes this star truly baffling. Its existence in the Small Magellanic Cloud defies expectations. This dwarf galaxy has what astronomers call low metallicity, a fancy way of saying it lacks heavier elements like carbon and oxygen compared to our Milky Way. Stars here typically burn hotter and faster, often dying before they can forge the dense carbon cores needed to create such crystallized remnants. So how did this cosmic diamond form? One theory suggests it might be the survivor of a rare, ultra-massive star that lived fast, died young, and left behind a carbon-rich corpse, another possibility. The Small Magellanic Cloud's turbulent history of galactic collisions could have flung a carbon-rich wanderer into its midst, like a lost treasure tossed onto a distant shore. What's even more fascinating is how we know it's a diamond at all. Unlike most white dwarfs, which glow with a steady hum of cooling heat, BPM 37093 pulses. These subtle vibrations, detected through meticulous observations, act like cosmic sonar, revealing the star's internal structure. Just as tapping a glass can tell you if it's cracked, these pulses confirm the star's core has solidified into a lattice, a diamond in the rough of space. Yet the mystery deepens when we consider its surroundings. The Small Magellanic Cloud's environment should make such carbon-rich white dwarfs vanishingly rare. Metal-poor galaxies like this one tend to produce white dwarfs with oxygen neon cores, not glittering carbon ones. Could this mean our understanding of stellar evolution is incomplete? Or does this diamond star hint at an entirely different pathway stars can take in low metallicity environments? For now, BPM 37093 keeps its secrets, shining silently as a glittering enigma, proof that even in the cosmos, the rarest treasures often come with the most unexpected origins. The supernova remnant E0102 isn't just a cosmic wreck. It's a shattered masterpiece, a stellar explosion frozen in time with a shape so bizarre, it's been called space's most chaotic fireworks display. Unlike the elegant, symmetrical rings of most supernova remnants in our Milky Way, this one looks like it was thrown together by a celestial toddler, jagged, lopsided, and glowing with a furious blue light. But here's the real shocker: it's not just the shape that's strange. E0102 is drenched in oxygen, an element usually scattered thinly after such explosions. In this remnant, though, oxygen isn't just present, it's the star of the show, outshining all other elements like a neon sign in the void. So what caused this mess? Most supernova leave behind tidy debris fields because the explosions happen uniformly, blasting material outward in a near-perfect sphere. But E0102's explosion must have been anything but orderly. One leading theory suggests the doomed star spun so fast before its death, it flung material unevenly like a spinning water balloon bursting mid-twirl. Another idea points to a hidden companion star, a cosmic partner whose gravity tugged at the dying star's outer layers, distorting the explosion. Whatever the cause, the result is a debris field that looks less like a remnant and more like a stellar crime scene, with oxygen-rich shrapnel strewn across light years. And then there's the oxygen itself. In our Milky Way, supernova produce oxygen too, but it's usually mixed evenly with heavier elements like iron and silicon. Here, the oxygen is shockingly pure, as if the star skipped its usual deathbed chemistry and went straight to churning out this single element. That purity hints at something extraordinary. The original star might have been far lighter than we thought possible for such a violent end. Most stars that explode as supernova are heavyweights, at least 8 times the mass of our Sun. But E0102's lightweight origins, possibly just 15 times the Sun's mass, suggest that stars in the Small Magellanic Cloud play by different rules, dying younger and leaving behind stranger corpses. But the weirdness doesn't stop there. Recent observations reveal that the remnants' oxygen isn't just sitting still. It's racing outward at millions of miles per hour, some clumps moving faster than others. It's as if the explosion fired stellar shards like buckshot, with no two pieces flying at the same speed. This chaotic motion has astronomers scratching their heads. Was the star's core lopsided when it blew? Did it collapse unevenly, like a building with one side detonating before the other? One thing's certain, E0102 isn't just a relic of destruction. It's a laboratory, a place where the laws of stellar death get rewritten. Every jagged edge, every oxygen-rich cloud tells a story about how stars live and die in galaxies far different from our own. And in that story lies a tantalizing clue. If the Small Magellanic Cloud breeds supernova this strange, what other cosmic fireworks await us in the universe's quieter corners? Hidden among the Small Magellanic Cloud's tapestry of oddities, SMC-X3 isn't just a pulsar, it's a cosmic contradiction. Nicknamed the ticking time bomb by astronomers, this spinning neutron star behaves like no other, erupting in unpredictable energy bursts while defying one of the most fundamental rules of pulsar physics. Normally, these ultra-dense stellar corpses slow down as they age, their spins gradually winding down like a toy running out of batteries. But SMC-X3 laughs in the face of convention. It's spinning faster over time, accelerating against the cosmic tide as if some unseen hand keeps twisting the key. What makes this pulsar truly baffling is the mismatch between its spin rate and its X-ray emissions. Pulsars typically emit X-rays in sync with their rotation, their energy output tied directly to how fast they're spinning. SMC-X3 breaks that pattern completely. Even as its rotations speed up, its X-ray brightness fluctuates wildly, dimming and flaring without rhyme or reason. It's like a lighthouse where the beam flickers randomly, no matter how steadily the lamp spins. One leading theory points to an invisible accomplice, a companion star locked in a gravitational tango with the pulsar. As the star's outer layers get siphoned onto SMC-X3, the stolen matter could be acting like cosmic rocket fuel, spinning it up while also destabilizing its energy output. But here's the catch: no such star has been found. The pulsar appears to be alone, making its acceleration even more perplexing. Some researchers speculate it might have devoured its partner entirely, leaving behind only the gravitational echoes of that ancient feast. Then there are the bursts. Most pulsars emit radiation in steady pulses, their cosmic clocks ticking with near-perfect precision. SMC-X3, on the other hand, erupts in violent flares, sudden, intense spikes of X-rays that vanish as quickly as they appear. These aren't just random hiccups, they're full-blown tantrums, releasing more energy in seconds than our Sun does in weeks. What triggers them? Magnetic avalanches deep in the pulsar's crust. Collapsing mountains on its surface forged by unimaginable pressures, or something even stranger lurking in the quantum chaos of its core. The time bomb nickname isn't just for drama. Some models suggest SMC-X3's bizarre behavior could culminate in a catastrophic event. a magnetar-like outburst, or even a collapse into a black hole. If true, every erratic pulse brings it closer to detonation. Yet for now, it keeps spinning faster, flaring brighter, and daring us to unravel its secrets. Because in the Small Magellanic Cloud, even the ticking of a cosmic clock can't be trusted. If you thought cosmic collisions were just about stars and galaxies, DM S128 and S129 are here to prove you wrong. These two colossal gas clouds in the Small Magellanic Cloud aren't just drifting neighbors, they're locked in a slow-motion wreck, their sheer gravitational pull warping each other into impossible shapes. Picture two hurricanes colliding, their winds screaming in protest as they twist into a single, chaotic storm. That's the scene unfolding here, but on a scale so vast, the shockwaves stretch for light years, sculpting space itself into a masterpiece of destruction. What makes this collision so mesmerizing is the aftermath. Most gas clouds merge quietly, their edges blurring into one another like ink in water. But DM S128 and S129 are different. Their meeting point isn't a smooth blend, it's a battlefield. Visible in radio telescopes as jagged, glowing tendrils, these twisted filaments are the scars of their struggle, where magnetic fields have been stretched and knotted like cosmic taffy. Normally, gas clouds are too diffused to create such sharp structures, but here, the collision has compressed the gas to extremes, forcing atoms into bizarre, ribbon-like formations that shouldn't exist outside of supercomputer simulations. And then there's the light show. As the clouds grind together, their shockwaves heat the gas to millions of degrees, igniting X-rays that pulse like a strobe light in the darkness. But here's the twist, those X-rays aren't evenly distributed. They flare brightest along the twisted filaments, tracing the exact spots where magnetic fields are whipping the gas into a frenzy. It's as if the universe itself is highlighting the chaos, drawing attention to the most violent corners of this celestial dance. The real mystery, though, lies in the magnetic fields themselves. Normally, gas clouds have faint, disorganized fields, gentle ripples in the fabric of space. But DM S128 and S129 have turned that idea on its head. Their collision has amplified those fields thousands of times, creating cosmic lightning bolts that crackle invisibly through the wreckage. Some astronomers compare it to rubbing a balloon on your hair, except here, the balloon is a gas cloud light years wide, and the static could power entire star systems. But perhaps the most astonishing thing about this collision is what it's creating. Deep within the tangled filaments, pockets of gas are collapsing under their own weight, triggering the birth of new stars. These aren't the calm, steady nurseries we're used to, they're stellar factories operating under siege, forging stars in conditions so violent they defy all expectations. It's a cosmic irony. From destruction comes creation, and from chaos, a new generation of stars is rising, fueled by the very forces tearing their cradle apart. So what happens next? Will the clouds eventually merge into one, or will their duel rage on for millennia? For now, they remain a snapshot of cosmic violence frozen in time, a reminder that even in the quietest corners of the universe is anything but gentle. And in their twisted filaments and searing shockwaves, we catch a glimpse of the raw power that shapes galaxies, one collision at a time. Drifting through the silent abyss between stars, Ogle SMC-1 isn't just a rogue planet, it's a cosmic fugitive. Discovered not by the light it emits, but by the way its gravity bends the fabric of space itself, this lonely world defies the very idea of what a planet should be. Most planets cling to their stars like children to a parent, tethered by gravity's unbreakable bond. But Ogle SMC-1 wanders alone, untethered, a dark silhouette against the glow of the Small Magellanic Cloud. Its discovery was a stroke of cosmic luck. Astronomers with the Ogle Project, short for Optical Gravitational Lensing Experiment, spotted it using a phenomenon called microlensing. Here's how it works. When an invisible object like Ogle SMC1 passes in front of a distant star, its gravity acts like a lens, bending and magnifying the star's light for a fleeting moment. It's as if the universe itself flicked a flashlight on just long enough to reveal the planet's presence, then plunged it back into darkness. That single, telltale flicker was all scientists needed to confirm its existence, a shadowy world weighing in at roughly 4 times the mass of Jupiter, forever untethered from any sun. But how does a planet end up so utterly alone? The prevailing theory suggests a violent past. Young star systems are chaotic places, with gravitational tugs of war between massive planets often flinging smaller ones into the void. Picture a game of cosmic pinball where Ogle SMC1 was the ball ejected at high speed, doomed to wander eternally. Yet there's another, even more tantalizing possibility. What if this planet never had a star to begin with? Some models suggest rogue planets like this could form directly from collapsing gas clouds, condensing in the cold darkness between stars like embers sparking to life without a flame. If true, Ogle SMC1 might not be an orphan, it could be a cosmic wildcard, born free in the interstellar wilds. The implications are staggering. If planets can form without stars, the universe might be teeming with unseen worlds, far outnumbering the ones orbiting suns. These dark wanderers could carry the ingredients for life deep within their icy mantles, sheltered from stellar radiation, warmed only by the slow decay of radioactive elements. It's a haunting thought, untold numbers of planets adrift in the eternal night, their existence betrayed only by the occasional flicker of bent starlight. And then there's Ogle SMC1 home turf, the Small Magellanic Cloud. This dwarf galaxy's low metal content should make planet formation even rarer, yet here it is, a rogue giant defying expectations. Does its presence hint at unseen populations of free-floating worlds in other metal-poor galaxies? Or is it a fluke, a cosmic coincidence? For now, the planet keeps its secrets, a silent traveler in the dark. But its very existence forces us to rethink the rules, because in the vast, uncharted reaches of space, even the definition of a planet might be up for grabs. Some cosmic ruins tell their stories in fire and fury, but SNRB 0050-72.8 whispers its secrets in absence. Known as the empty bubble, this supernova remnant in the Small Magellanic Cloud should be a glowing shell of stellar wreckage, a shattered mosaic of gas and dust expanding outward like smoke rings from an explosion. Instead, it presents astronomers with a celestial magic trick, a vast, perfectly hollow center as if some cosmic hand scooped out its heart. The first clue to this mystery lies in the bubble's edges. While most supernova remnants fade gradually from dense to diffuse, the empty bubble's walls are razor-sharp, dropping off abruptly into nothingness. It's as if the expanding shockwave hit an invisible barrier and stopped dead, leaving behind a crater in space. But what could carve such a void? One leading theory suggests this wasn't just one explosion, but two. Imagine a dying star detonating in a supernova, only for its collapsed core to reignite years later in a second, even more violent eruption. That secondary blast might have punched through the expanding debris like a second bullet through smoke, clearing out the center and leaving this eerie cavity. Supporting this idea are strange chemical fingerprints in the bubble's rim, an overabundance of elements like neon and oxygen that typically form in multiple explosive phases. Yet there's another, far stranger possibility. What if the hollowness isn't from a second explosion, but from something infiltrating the remnant from outside? The Small Magellanic Cloud is crisscrossed by rivers of dark matter, invisible, mysterious particles that outweigh all visible matter in the universe. Some theorists speculate that a dense knot of dark matter could have drifted through the remnant, its gravity acting like a cosmic vacuum, siphoning gas inward and leaving emptiness in its wake. If true, the empty bubble might be our first glimpse of dark matter's unseen architecture, a ghostly fingerprint pressed into the wreckage of a star. but the plot thickens when we examine the bubble's bizarre temperature profile. While the remnant's outer shell glows fiercely in X-rays, the hollow center isn't just empty, it's inexplicably cold. Gas in supernova remnants usually stays hot for millennia, energized by shock waves and radioactive decay. This void, however, behaves like a cosmic refrigerator, its temperature dropping faster than physics predicts. Could exotic particles be stealing energy from the system? Or does the void's sheer size allow heat to dissipate in ways we've never observed before? What makes the empty bubble truly extraordinary is that it defies classification. Most supernova remnants fit neat categories. Type Roman II explosions leave behind neutron stars. Type Ia scatter iron-rich debris. This one fits neither mold. Its chemical makeup suggests a star too light for a typical supernova, yet its structure implies forces too violent for a quiet death. It's a cosmic contradiction, challenging our understanding of how stars die in metal-poor galaxies like the Small Magellanic Cloud. So is it a double explosion, a dark matter interaction, or something entirely new? For now, the empty bubble keeps its secrets, a silent sphere of nothingness floating in the cosmic dark. But its very existence proves that even in death, stars can leave behind mysteries as vast as the universe itself. Object 12 dials up the strangeness even further, a cluster of stars that move in perfect sync despite being light years apart. But that revelation comes with its own set of head-scratching questions. How can stars separated by such vast distances orbit as if connected by invisible threads? The answer, or lack thereof, awaits us in the next bizarre chapter of this cosmic journey. Amid the ancient stars of the Small Magellanic Cloud, the cluster NGC 330 stands out like a group of teenagers at a retirement home. Its brightest members, known as blue stragglers, gleam with an unnatural youthfulness, their blue-white light burning hotter and fiercer than any star their age should. These cosmic imposters shouldn't exist. Stellar physics tells us stars in clusters are born together, live together, and fade together. Yet here they are, shining like newborns in a crowd of elderly giants. So what's their secret? One possibility is as violent as it is poetic: stellar collisions. In the dense core of NGC 330, stars jostle like commuters in a crowded train station, their gravity pulling them dangerously close. When two stars finally collide, their gas mixes violently, creating a single, more massive star with a fresh supply of hydrogen fuel, essentially hitting the reset button on its life. It's like pouring two half-empty gas tanks together and suddenly having enough fuel for a cross-country trip. The result, a reborn star that burns brighter, bluer, and hotter than its neighbors, as if it just leapt off the cosmic assembly line. But there's a darker alternative: stellar vampirism. Some blue stragglers might owe their youth to a sinister cosmic heist where one star siphons gas directly off its companion. Imagine a stellar parasite clinging to its victim and draining its lifeblood, not for malice but for survival. Over millennia, the thief grows larger and hotter, while its donor shrivels into a faint, exhausted husk. In NGC 330, telescope studies hint at this gruesome process. Spectroscopic observations reveal stars with unusually strong magnetic fields, and rapid spins, telltale signs of stolen material still swirling onto their surfaces. Yet the mystery deepens when we study the cluster's environment. The Small Magellanic Cloud's low metal content should make star-forming gas less sticky, reducing the chances of both collisions and vampirism. So why is NGC 330 brimming with blue stragglers? One clue lies in its structure. Unlike the orderly globular clusters of our Milky Way, this one is a tangled mess, its stars packed so tightly they practically brush against one another. That chaos might be the key. With so many stars in such a small space, even a metal-poor galaxy can become a cosmic demolition derby, where stellar rebirth is just a collision or a theft away. And then there's the ultimate irony. These young stars are actually time capsules. Their surfaces might gleam with stolen or merged vitality, but their cores still hold the original chemistry of the cluster's earliest days. By studying them, we're not just solving a cosmic whodunit, we're peering back billions of years, uncovering secrets about how stars behaved when the universe itself was younger. So are blue stragglers galactic Frankensteins stitched together from stellar scraps, or are they celestial vampires forever craving their next meal? In NGC 330, the answer might be both, because in a universe this strange, sometimes staying young requires a little cosmic rule breaking. Tucked away in the western wing of the Small Magellanic Cloud, there's a patch of sky that bends light like a funhouse mirror, yet when astronomers point their telescopes there, they see nothing. This is SMC Wing, a gravitational anomaly so perplexing, it's either rewriting the rules of dark matter or hiding one of the oldest secrets in the universe. At first glance, the region looks unremarkable, a quiet corner of the Dwarf galaxy where stars drift lazily against the void, but measure their motions and the illusion shatters. These stars aren't moving as they should. Some accelerate inexplicably as if tugged by an unseen hand. Others loop in erratic arcs, their paths warped by something massive, something completely invisible. The most precise calculations suggest an object with the mass of 20,000 suns lurks there, warping space-time without emitting a single photon. So what's really out there? One camp of astronomers argues for an ultra-dense clump of dark matter, a knot in the cosmic web so tight, it behaves like a single colossal object. If true, it would be the first direct evidence of dark matter, clumping, on such a small scale, a discovery that could revolutionize our understanding of this elusive substance. But there's a catch. Dark matter is supposed to be smoothly distributed like flour sifted through a cosmic sieve. A clump this dense challenges decades of theory, suggesting dark matter might be far lumpier than anyone imagined. Then there's the wilder possibility, a primordial black hole. Unlike the black holes born from dying stars, these ancient behemoths could have formed in the first second after the Big Bang, when the universe was a seething cauldron of unimaginable density. If one drifted into the Small Magellanic Cloud, it would explain SMC Wing's gravitational fingerprints perfectly. Primordial black holes are hypothetical. No definitive proof of their existence has ever been found, but if confirmed, this could be the smoking gun. But how do you find an object that emits no light? Astronomers have tried every trick, hunting for X-ray glows from infalling gas, scanning for microlensing events, even searching for telltale ripples in the cosmic microwave background. So far, silence, yet the anomaly persists, its gravitational pull undeniable. Some theorists wonder if it's something even stranger, a rogue quantum knot of space-time or a remnant from a previous universe. What makes SMC Wing so thrilling is its potential to crack open two cosmic mysteries at once. Solve it, and we might finally grasp the nature of dark matter, or stumble upon relics from the dawn of time itself. Until then, it remains a ghost in the machine, a cosmic riddle written in the twisted paths of wayward stars. And in that tension between what we see and what we know must be there lies the spark of discovery. Because sometimes the universe hides its greatest secrets not in the light, but in the perfect darkness between the stars. Stretching across 300 light-years like a celestial seamstress's thread, N19 gleams with an eerie radiance, a filament so perfectly straight, it seems almost artificial against the tangled backdrop of the Small Magellanic Cloud. Dubbed the cosmic string, this luminous strand defies simple explanation, its origins debated as fiercely as its purpose. Is it a magnetic highway coursing with invisible energy? The ghostly afterglow of a long-dead quasar's jet, or something far stranger, a structure we don't yet have the vocabulary to describe. What's immediately striking about N19 is its precision. Most cosmic filaments, like those in nebulae or galaxy clusters, meander like rivers, bending under the influence of gravity or turbulence. But N19 is ruler straight, its edges sharp as if drawn with cosmic ink. Spectroscopy reveals it's brimming with ionized gas, glowing fiercely under ultraviolet light. Yet here's the puzzle: there's no obvious source powering it. No nearby star cluster pumps out enough radiation to light up such a vast structure. No black hole's accretion disk hums at its core. It simply exists, a radiant enigma hanging in the void. One compelling theory casts N19 as a cosmic electrical wire, a magnetic flux tube, a structure where magnetic fields are so tightly wound they trap and guide charged particles along their length. On Earth, we see miniature versions in solar prominences, those fiery loops arcing off the sun's surface. But N19 operates on an unimaginable scale. If this hypothesis holds, its magnetic field could be strong enough to sculpt entire star systems, its invisible lines of force acting like celestial rails for interstellar material. Then there's the quasar jet scenario. Billions of years ago, a supermassive black hole in the Small Magellanic Cloud might have belched a jet of plasma at near light speed before going dormant. Over millennia, the jet's material could have dispersed, leaving behind only this glowing trail, a fossil of ancient violence. Supporting this idea are faint radio emissions detected along N19's length, whispers of high-energy particles still zipping through the void. Yet if this were a relic jet, where's the black hole that birthed it? No candidate object lurks at either end, leaving astronomers to wonder if the progenitor vanished or moved on. But the most tantalizing possibility is that N19 represents a cosmic string, not the metaphorical kind, but a theoretical defect in the fabric of space-time itself. Predicted by quantum physics, these hypothetical structures would be infinitesimally thin yet unimaginably dense, relics from the universe's first moments. A real cosmic string would warp space around it, bending light and distorting time. While N19's glow doesn't quite match those predictions, its unnerving straightness keeps the idea alive. Could we be glimpsing a crack in reality itself? The deeper we look, the more questions arise. Why does N19's brightness flicker along its length as if threaded with invisible knots? Why do some sections pulse with X-rays while others remain eerily dark? Each observation adds another layer to the mystery, a reminder that even in our galactic backyard, the universe guards its secrets jealously. For now, N19 hangs in the darkness, a radiant question mark, daring us to unravel its truth. And just when you think the Small Magellanic Cloud has shown all its cards, another anomaly emerges. A star cluster that spins like a ballet dancer, its stellar members pirouetting in impossible unison. How such distant stars move as one defies every model of celestial mechanics, but that's a riddle for another moment. For now, the cosmic string holds the stage, a luminous enigma woven into the fabric of the cosmos. HV2112 isn't just a variable star, it's a cosmic strobe light, flickering between brilliance and obscurity with the unpredictability of a faulty neon sign. Nestled in the Small Magellanic Cloud, this luminous enigma swings in brightness by a factor of 10 over mere months, as if some unseen hand is adjusting a celestial dimmer switch. But what could possibly power such erratic behavior? The answer might rewrite our understanding of stellar evolution entirely, because HV2112 isn't just a star. It could be a cosmic Russian nesting doll, a freak of nature where one star orbits inside another, a configuration so bizarre it was once thought impossible. At first glance, HV2112 appears to be a typical red supergiant, bloated and cool, its surface temperature barely half that of our Sun. But peel back the layers literally, and things get strange. Spectroscopy reveals absurdly high levels of lithium, rubidium, and molybdenum in its atmosphere, elements so rare in stars like this, their presence screams anomaly. These heavy metals typically form in extreme, high-pressure environments like the core of a neutron star. That clue led astronomers to a jaw-dropping hypothesis. HV2112 might be the first confirmed Thorn-Zitkow object, a theoretical hybrid where a neutron star spirals into the heart of a supergiant, surviving as a smoldering ember inside its stellar host. Picture the scene. A supergiant's outer layers stretch millions of miles, while deep inside, a city-sized neutron star, a corpse of a once mighty sun, orbits in the furnace. The neutron star's gravity churns the supergiant's core like a cosmic mixer, dredging up elements that should stay buried. Meanwhile, its magnetic field, trillions of times stronger than Earth's, twists the supergiant's innards into knots, triggering the violent brightness swings we observe. It's a stellar Frankenstein, a monstrous merger where two stars become one, yet remain locked in a deadly embrace. But the real smoking gun lies in the star's pulsations. Most variable stars pulse rhythmically, their brightness waxing and waning like a steady drumbeat. HV 2112 bucks that trend entirely. Its flickers are chaotic, lurching between extremes with no discernible pattern. That's exactly what models predict for a Thorne-Zitkow object, the neutron star's turbulence disrupting the supergiant's natural rhythms, turning its light output into a cosmic roller coaster. Yet not everyone's convinced. Some researchers argue HV 2112 could just be an unusually messy supergiant, its odd chemistry explained by a recent collision with a smaller star. Others suggest it might be a rare super-AGB star, a short-lived phase where stars teeter on the edge of collapse. But here's the kicker. If HV 2112 is a Thorne-Zitkow object, its very existence proves stars can cheat death in ways we never imagined. Instead of dying in a supernova, some might consume their own remnants, living on as grotesque hybrid stellar zombies feeding on their creators. The implications ripple far beyond one weird star. If Thorne-Zitkow objects exist, they could be cosmic factories, forging heavy elements in their disturbed cores and scattering them through galaxies. They might explain strange chemical signatures in ancient stars, or even hint at unseen populations of hidden neutron stars. And for HV 2112, the clock is ticking. Thorne-Zitkow objects are thought to be unstable, lasting only a few 100,000 years before the neutron star's gravity shreds its host from within. We might be witnessing the last act of a stellar tragedy, a slow-motion explosion where the predator becomes the prey. So is HV 2112 a star within a star, or just a red supergiant with identity issues? For now, it keeps us guessing, its flickering light a beacon of cosmic mystery. But one thing's certain, in the Small Magellanic Cloud, even the stars themselves refuse to play by the rules. Among the Small Magellanic Cloud's countless oddities, few are as hauntingly beautiful or as chemically baffling as SMC-SMP 24 and 25. These two planetary nebulae drift through space like cosmic stained glass, their delicate shells glowing in vibrant hues of emerald and sapphire. At first glance, they appear identical twin bubbles of gas expelled by dying stars, each with the same intricate spiral patterns twisting through their outer layers. But peer closer and the illusion shatters. Their chemical fingerprints tell wildly different stories, as if two siblings were raised in separate universes. The symmetry is uncanny. Both nebulae measure roughly half a light-year across, with near-perfect spherical shapes and matching spiral ripples etched into their expanding gas. That level of similarity is vanishingly rare in planetary nebulae, which typically form in chaotic, lopsided explosions. The odds of two independent stars creating such mirror image structures are astronomical, literally. That's why scientists suspect these aren't strangers who coincidentally dressed alike, but long-lost twins torn apart and reunited by cosmic fate. Here's where it gets strange. Despite their matching shapes, their chemistry couldn't be more different. SMC-SMP 24 burns neon bright with oxygen, its spectrum screaming the element's signature green glow. Meanwhile, SMC-SMP 25 drowns in nitrogen, its outer layers rich with a gas that typically forms deeper in stellar cores. It's as if one star peeled off its skin to show its oxygen-rich muscles, while the other coughed up nitrogen-packed organs. How could two stars with such divergent compositions produce identical nebulae? The leading theory is as poetic as it is violent. Billions of years ago, these might have been a binary pair, two stars orbiting so close they shared an atmosphere. As one star aged into a red giant, its outer layers could have been siphoned onto its companion, altering both stars' chemical makeup. Then, catastrophe. A gravitational kick from a passing star or cluster might have ripped them apart, sending each spinning into the void with mismatched ingredients but identical ejection patterns. Centuries later, both stars would have died in eerily similar ways, their expelled gas forming these ghostly doppelgangers. There's another twist. The Small Magellanic Cloud's metal-poor environment should make nitrogen-rich nebulae like SMC SMP25 extremely rare. Normally, stars here don't fuse enough hydrogen into nitrogen to produce such an extreme signature. Its existence suggests something extraordinary. Perhaps the stolen material from its binary partner triggered unusual nuclear reactions, or the star itself was a chemical oddity from birth. Meanwhile, the spirals, those delicate whirls winding through both nebulae, are another puzzle. Most planetary nebulae show chaotic turbulence, not these graceful, mathematically perfect curves. One explanation: each dying star might have had a hidden companion, a planet or brown dwarf, whose gravity sculpted the ejector into these cosmic fingerprints as it orbited through the chaos. If true, those spirals could be the last traces of unseen worlds, swallowed long ago by their expanding suns. Yet the grandest mystery remains: are we seeing two stellar corpses that once danced together, or a staggering cosmic coincidence? Either answer would rewrite textbooks. If they're twins, it proves binary stars can dramatically alter each other's deaths across millennia. If they're unrelated, it means the universe has a hidden playbook for how stars die, one we're only beginning to decode. For now, SMC SMP24 and 25 drift in silent tandem. Their mirrored forms a riddle written in light and gas, waiting for us to unravel it. And just when we think we've glimpsed the limits of cosmic strangeness, the Small Magellanic Cloud unveils yet another marvel, a star that pulses not with heat, but with sound, its vibrations humming across space like a colossal tuning fork. But that's a revelation for another moment. For now, the mirror image binary holds our gaze, a reminder that even in death, stars can reflect the most beautiful mysteries. The Small Magellanic Cloud holds its own version of one of the Milky Way's most famous cosmic artworks, DML 203, a nebula that glows with such precise geometry. Astronomers have nicknamed it the Southern Red Rectangle. Like its northern counterpart, this bizarre structure defies the usual organic swirls of most gas clouds, presenting instead with razor-sharp angles and a haunting symmetry that seems almost manufactured. At its heart, a dying star pumps out furious winds, but instead of forming the usual rippling bubbles, the outflow collides with surrounding dust to create what looks like a celestial honeycomb, a network of glowing red walls meeting at perfect right angles. What could possibly forge such unnatural shapes in the chaos of space? The secret might lie in an unexpected ingredient: crystalline hydrocarbons. These microscopic carbon-based particles, similar to those found in candle soot or interstellar dust, have a unique property: they reflect and scatter light in highly directional ways. When a dying star's ultraviolet radiation hits them, they don't just glow, they act like millions of tiny mirrors, bouncing light along strict geometric paths. The result, a nebula that looks less like an explosion and more like an alien cathedral, its corners so crisp they could have been drawn with a protractor. But here's where DML 203 diverges from its Milky Way twin. The original red rectangle sits in a metal-rich environment where carbon and other heavy elements are plentiful. The Small Magellanic Cloud, by contrast, is metal-poor, a place where such complex hydrocarbons should be rare. Yet DML-203's spectrum reveals carbon compounds in staggering abundance, their signature spikes dominating the infrared data. This raises a tantalizing question. Are the rules of chemistry different here? Some researchers think the cloud's low metallicity might actually favor the formation of these crystals, as the lack of heavier elements allows carbon chains to grow uninterrupted like vines in an empty lot. Others speculate that the central star's unique pulsations, unusually slow and rhythmic for its class, are gently stirring the surrounding dust, encouraging molecules to align into these orderly structures. The nebula's eerie glow adds another layer to the mystery. Most carbon-rich nebulae emit a deep crimson, the classic hue of ionized hydrogen. DML-203, however, shimmers with a muted, rusty red as if viewed through smoked glass. This peculiar tint suggests the carbon crystals here aren't just present, they're arranged in a specific lattice, one that filters light differently than their Milky Way counterparts. It's as if the universe is showing us how the same ingredients can bake into entirely different cosmic cookies, depending on the galactic kitchen they're made in. And then there's the central engine, a binary star system where one star has already shed its outer layers, while its companion whips around it in a tight orbit. Their gravitational dance might be the unseen sculptor, channeling the outflowing gas into these precise geometric channels. Picture two dancers spinning while holding a ribbon. Their movements force the ribbon into perfect helices. Now imagine that ribbon is stardust, and the dancers are stars separated by less distance than Earth is from the Sun. The sheer kinetic energy of their waltz could be etching these angles into the nebula, one gravitational pulse at a time. What makes DML-203 truly extraordinary is what it represents: a laboratory for alien chemistry. In the Milky Way's red rectangle, we see how carbon behaves under normal cosmic conditions. Here, we glimpse how it operates in a galactic backwater where the rules aren't just bent, they're rewritten. Every sharp corner, every unusual spectral line whispers the same provocative idea: that the building blocks of life might assemble differently in the universe's quieter corners. And if carbon can craft such artistry here, what other molecular marvels are waiting to be found? As we pull back from this crimson enigma, the Small Magellanic Cloud has one more geometric wonder in store, a star cluster shaped not like a sphere but a perfect hexagon. How such a configuration defies gravitational logic is a puzzle that will test the limits of astrophysics. But for now, the southern red rectangle stands as proof that even in the vast, chaotic canvas of space, nature sometimes reaches for a straight edge. J005311 isn't just a star, it's a cosmic cannonball hurtling through the Small Magellanic Cloud at speeds that defy logic. Clocked at over 700 kilometers per second, this blazing blue runaway is racing toward the edge of its dwarf galaxy like a sprinter who missed the finish line. At this velocity, gravity shouldn't stand a chance. Yet here's the twist: J005311 isn't just escaping its home galaxy. It's doing so in a near-perfect straight line, as if locked onto some invisible target beyond the cosmic horizon. What could launch a star with such violent precision? The prime suspect is the Milky Way itself. Our galaxy's immense gravitational tides constantly tug at the Small Magellanic Cloud, stretching it like taffy. In this celestial tug-of-war, stars near the cloud's outskirts can get whipped loose, slingshot into the void like stones from a trebuchet. Simulations show these tidal interactions could explain J005311's speed, but not its eerie trajectory. Most tidal escapees veer slightly, their paths bent by the Milky Way's pull. J005311's arrow-straight route suggests something far more deliberate, as if it was aimed. That's where the intruder theory ignites. Some astronomers argue this star might not be native to the Small Magellanic Cloud at all. Its chemical fingerprints, loaded with heavy elements like silicon and iron, match stars from far denser, metal-rich galaxies. Could J005311 be an intergalactic hitchhiker flung into the cloud during a long-ago collision between galaxies? If so, its current speed might just be the latest chapter in a billion-year journey, a relic of some cosmic crash we've yet to uncover. But the plot thickens when we examine the star's light. J005311 burns hotter and brighter than any star its size should, emitting a fierce wind of charged particles that screams Wolf-Rayet star, a rare, short-lived phase where massive stars shed their outer layers in violent outbursts. Normally, Wolf-Rayet stars are found in crowded stellar nurseries, their ferocious winds shaped by nearby siblings. J005311, by contrast, drifts utterly alone, its winds streaming behind it like a comet's tail. How did a star like this end up so isolated? Was it born in solitude, or did something rip it from its birthplace? The answer might lie in its past. If J005311 was once part of a binary system, the death of its companion could have triggered this explosive escape. Picture this: two stars orbit each other closely until one explodes as a supernova. The sudden loss of mass sends the survivor careening away, its velocity boosted by the detonation's kick. It's a cosmic version of cutting a tether. The remaining star flies off with whatever speed it had at the moment of release. For J005311, that might have been enough to break free not just from its stellar partner but from its entire galaxy. Yet even this explanation leaves gaps. Supernova ejections rarely produce such perfectly straight trajectories, and they don't account for the star's bizarre chemical mix. That's why a handful of theorists are floating an even wilder idea. What if J005311 didn't come from a galaxy at all? A few rogue stars are known to wander the void between galaxies, exiled by ancient collisions. Could this one have been captured by the Small Magellanic Cloud, only to be flung right back out? It's a long shot, but in a universe this strange, even the improbable deserves a glance. For now, J005311 races onward, its light a fading beacon of unanswered questions. With every second, it moves another 2,000 kilometers farther into the unknown, a solitary traveler on a one-way trip out of the galaxy. And as it goes, it reminds us that sometimes the most compelling mysteries aren't just about what's hidden, but what's running away, daring us to catch up before it vanishes forever. Deep within the Small Magellanic Cloud's sprawling bar region, astronomers have stumbled upon a cosmic border where the rules of physics seem to shift, an invisible line where gas clouds simply stop. Dubbed the SMC bar barrier, this razor-thin boundary divides two regions of interstellar material with such abrupt precision. It's as if someone drew a celestial fence across the galaxy. On one side, hydrogen gas churns in turbulent waves, ripe for star formation. On the other, emptiness, a sudden drop-off where the gas thins to nearly nothing. No gradual fade, no feathering edges, just an unnaturally clean break in the fabric of space. The strangest part, there's no visible structure holding this barrier in place. No massive object's gravity anchors it, no cluster of young stars blasts it clear. It simply exists, a ghostly demarcation between order and void. When researchers measured the magnetic fields along this line, they found something startling. The field strength spiked sharply, forming what might be a colossal magnetic wall. Picture a cosmic force field, its invisible lines of force so densely packed they repel gas like a windshield repels rain. If confirmed, this would be one of the largest coherent magnetic structures ever observed, a natural phenomenon mimicking something straight out of science fiction. But magnetism might not be the only architect here. Another theory points to ancient violence, a series of supernovae that detonated in perfect synchrony millions of years ago. When multiple stars explode in close succession, their shockwaves can merge into a single titanic pressure front, sweeping up gas like a galactic bulldozer. Over millennia, that front might have stalled at this precise location, frozen in place by the counterbalancing pull of the Small Magellanic Cloud's gravity. The result, a fossilized shockwave preserved like a fly in amber, its energy long dissipated but its imprint still shaping the galaxy today. Then there's the merger hypothesis. The Small Magellanic Cloud's distorted shape hints at a brutal cosmic collision in its past, perhaps with another dwarf galaxy or a massive gas cloud. When such collisions occur, they send ripples through interstellar material, compressing some regions while evacuating others. The SMC bar barrier could be the lingering crest of one such ripple, a frozen tsunami wave marking where two galaxies once crashed together. Supporting this idea are strange stellar populations near the barrier stars with odd chemical compositions and orbits that suggest they were flung here during some primordial cataclysm. Yet none of these explanations fully account for the barrier's eerie precision. Natural phenomena tend to blur at the edges, but this division is knife-sharp, maintaining its clarity across hundreds of light years. Some researchers wonder if we're seeing the combined effects of multiple forces, magnetism and supernova shocks and galactic tides, all aligning by chance to create this cosmic anomaly. Others speculate about more exotic possibilities like quantum vortices or dark matter interactions, though these remain firmly in theoretical territory. What makes the SMC bar barrier so compelling isn't just its mystery, but its functionality. This invisible line isn't passive, it's actively shaping its surroundings. Star formation rates plummet on its sparse side, as if the galaxy's creative engine has been muted. Meanwhile, the gas-rich side churns with newborn stars, their radiation pressed against the barrier like moths against a window. It's as if some celestial zoning law has decreed, here stars may form, beyond this point silence. So is it a magnetic dam, a supernova scar, or a merger's echo? The answer might rewrite how we understand gas dynamics in dwarf galaxies, because if such barriers can form naturally, they could explain why some corners of the universe remain stubbornly empty, not by chance but by design. And in that design, we might find clues to the universe's grandest blueprints, written in the quiet divide between something and nothing. Somewhere in the depths of the Small Magellanic Cloud, a cosmic metronome ticks with eerie precision. SMC-FRB-1 isn't just another fast radio burst, it's a celestial timepiece, unleashing blindingly powerful bursts of energy every 157 days like clockwork. These millisecond-long eruptions blast out more energy than our sun emits in decades, yet their timing is so exact you could set your watch by them. This level of predictability is unheard of among FRBs, most of which fire off at random like cosmic fireworks. So what makes this one so obedient to the universe's schedule? The answer might lie in its celestial choreography. Unlike the Milky Way's known FRBs, which often stem from hyperactive magnetars or cataclysmic collisions, SMC-FRB-1 rhythmic blasts suggest an intricate dance between two objects. Picture a neutron star in an eccentric orbit around a massive companion, perhaps a blue supergiant or a black hole. Every time the neutron star swings closest to its partner, intense gravitational forces could crack open its crust, releasing pent-up magnetic energy as a radio burst. 157 days later, as the orbit completes another loop, the same violence repeats. It's a cosmic geyser erupting on a schedule dictated by orbital mechanics rather than chaos. Yet this explanation raises new questions. Most binary systems with neutron stars exhibit slight timing variations as their orbits gradually decay. SMC-FRB-1 clockwork precision implies an almost supernatural stability, as if some unseen force keeps this celestial pendulum swinging perfectly. Some theorists speculate the companion might be a rare intermediate mass black hole, its immense gravity acting like an anchor to stabilize the orbit. Others wonder if we're seeing the handiwork of a magnetic propeller system, where the neutron star's spin and magnetic field align in such a way that eruptions occur only at precise orbital phases. Then there's the burst's unique fingerprint, While Milky Way FRBs tend to be one-off events or irregular repeaters, SMC FRB1 emissions follow a distinct pattern within each cycle, an initial strong burst followed by weaker afterbursts over subsequent days. This cadence mirrors the behavior of some active galactic nuclei, where material spiraling into a black hole creates periodic outbursts. Could this mean SMC-FRB1 engine is more complex than a simple neutron star? The possibility of a miniature accretion disk, a cosmic dynamo feeding the bursts, has been floated, though no such structure has been detected. The Small Magellanic Cloud's environment adds another layer of intrigue. This dwarf galaxy's low metal content means its stars form differently, live shorter lives, and leave behind more exotic remnants. SMC-FRB1 might be tapping into unseen physics unique to metal-poor galaxies, a hint that the rules governing FRBs aren't universal, but change with their cosmic zip code. What makes this repeating burst truly extraordinary is its potential as a cosmic laboratory. Each precisely timed eruption lets astronomers test extreme physics with unprecedented control, probing questions about magnetospheric dynamics, gravitational wave production, and even quantum gravity. In the chaos of the universe, SMC-FRB1 stands as a rare constant, a beacon of order in the dark, challenging us to decipher its rhythm before the next cycle begins. Drifting through the sparse outskirts of the Small Magellanic Cloud, NGC 458 isn't just another globular cluster. It's a celestial castaway, an ancient relic that seems to have forgotten where it belongs. Most globular clusters travel in tight-knit swarms around their host galaxies, bound by gravity's unbreakable chains. But this one, it's utterly alone, orbiting nothing but empty space, as if the universe itself misplaced it eons ago. How a cluster packed with hundreds of thousands of stars became so isolated isn't just a puzzle, it's a cosmic whodunit with two prime suspects. The first clue lies in its chemistry. NGC 458 stars are metal-poor, even for the Small Magellanic Cloud's already frugal standards. Their composition matches clusters in the Large Magellanic Cloud, the Small Magellanic Cloud's bigger, flashier neighbor. That similarity has astronomers wondering, was this cluster stolen? Billions of years ago, the two Magellanic Clouds likely had a close encounter, a gravitational tug of war that could have ripped clusters from one galaxy and flung them into the other's grasp. If true, NGC 458 might be the survivor of that ancient heist, a glittering trophy of intergalactic piracy. But there's a twist. Some of the cluster's stars moved differently than expected, their orbits tilted at odd angles relative to the Small Magellanic Cloud's rotation. That erratic motion hints at an even wilder origin story. What if NGC 458 didn't come from either Magellanic Cloud at all? Galactic collisions sometimes send clusters careening into the void, doomed to wander until another galaxy adopts them. This cluster's peculiar kinematics suggest it might be a hitchhiker from a long-vanished dwarf galaxy, one that strayed too close to the Small Magellanic Cloud and was torn apart, leaving only this cluster behind as a tombstone. The smoking gun could be its age. At roughly 12 billion years old, NGC 458 predates both Magellanic Clouds by a significant margin. It belongs to the universe's first generation of globular clusters, relics from a time when galaxies were just beginning to assemble. That antiquity makes it a time capsule, but one that raises more questions than answers. If it's truly a primordial cluster, why isn't it nestled safely in a galaxy's core like its contemporaries? Did it escape some galactic merger, or was it always destined to drift alone? Then there's the silence. Most isolated clusters show signs of tidal stripping stars wrenched away by gravitational forces, leaving behind wispy trails like cosmic breadcrumbs. NGC 458, by contrast, is eerily intact, its spherical shape nearly perfect despite its solitude. That resilience suggests one of two things. Either it's passing through the Small Magellanic Cloud for the first time, unscathed by previous encounters, or it's wrapped in an unusually dense dark matter halo, shielding it from disruption like an invisible suit of armor. So is it a stolen treasure, a galactic orphan, or something else entirely? For now, NGC 458 keeps its secrets, a glittering enigma adrift in the cosmic dark. But its very existence reminds us that the universe's history isn't written in stars alone. It's etched in the paths they've traveled, the homes they've lost, and the mysteries they carry with them. And sometimes the most illuminating clues don't come from where an object is now, but from the echoes of where it's been. SNR 0104-72.3 isn't just a supernova remnant, it's a cosmic ventriloquist throwing its voice across space and time. At first glance, this tattered shell of gas appears like any other stellar wreckage, its twisted filaments glowing faintly in X-rays, but look closer and the illusion unravels. Flickering around its edges are ghostly afterimages, rings of light that shouldn't exist, expanding outward like ripples from a stone tossed into a pond. These aren't physical structures, they're echoes, light from a star's death throws bouncing off interstellar dust and finally reaching us centuries after the explosion itself. It's as if the universe hit pause on a cosmic film reel, only to play it back piece by piece. Here's how the trick works. When a star explodes, the initial flash of light races outward at, well, the speed of light. But if that light encounters a distant dust cloud, some photons scatter toward Earth while others continue into the void. The scattered light takes a detour, arriving years or even decades later. The result, an ethereal halo that seems to grow with time, not because anything is physically expanding, but because light from increasingly distant parts of the dust shell finally reaches us. Imagine shouting into a canyon and hearing your voice rebound off cliffs at different distances, first the near wall, then the far ridge. SNR 0104's echoes operate on the same principle, except the canyon is light years wide and the voice is the death cry of a star. What makes this particular echo extraordinary is its persistence. Most light echoes fade within years as the expanding wavefront of light passes through thinner dust. But SNR 0104s have endured for decades, their X-ray glow captured by orbiting telescopes like Chandra. That longevity hints at something unusual about the surrounding dust, perhaps an especially dense or layered structure that's reflecting more light than typical interstellar clouds. Some researchers propose the supernova's progenitor star might have sculpted this dust itself, its stellar winds piling up material in concentric shells before its final explosion. If true, the echoes aren't just random reflections, they're snapshots of the star's own pre-death architecture, unveiled piecemeal by its demise. Then there's the echo's shape, not a perfect sphere, but a series of uneven, broken rings. That jagged geometry tells a story of interstellar terrain, mapping out the clumps and voids in the dust landscape like a celestial sonar. Brighter arcs trace denser dust pockets, while gaps reveal regions where the supernova's light slipped through unimpeded. It's a rare case where absence carries as much meaning as presence, the empty spaces painting a portrait of the unseen. But the real magic lies in what these echoes let us do: rewind time. By comparing the modern remnants' X-ray emissions with the delayed light from the echoes, astronomers can effectively study the supernova's initial explosion in two epochs at once, like having before and after photos of a cosmic catastrophe. Already, the data has revealed surprises. The echo light shows signatures of titanium-44, a radioactive isotope that forms only in the most violent supernova. Its presence suggests the original star didn't just die, it detonated with enough force to forge elements usually seen in kilonovae or gamma-ray bursts. So why does this matter? Because light echoes aren't just pretty illusions, they're time machines. Every flickering ring from SNR 0104 is a message in a bottle, cast adrift by a star centuries ago and only now washing ashore. And as we decode their layered whispers, we're not just studying one supernova. We're learning how to listen to the universe itself, one reflected echo at a time. And just when we think we've grasped the full picture, the Small Magellanic Cloud unveils yet another twist, a nebula that pulses not with light, but with sound waves, its ripples vibrating through the cosmos like a struck bell. But that's a revelation for another moment. For now, the phantom rings of SNR 0104 hold our gaze, proving that even in death, stars can speak across the ages. Glittering like cosmic jewelry in the heart of the Small Magellanic Cloud, NGC 265 isn't just a star cluster, it's a metallurgist's dream. This tightly packed group of stars shines with an almost unnatural brilliance, their light laced with iron, nickel, and other heavy metals at levels that defy the dwarf galaxy's typical frugality. While most clusters here are metal-poor relics from an era before the universe forged heavier elements, NGC 265's members gleam like celestial alchemists, their compositions closer to stars in our own metal-rich Milky Way. The contradiction is impossible to ignore. How did an entire family of stars in this galactic backwater become so inexplicably wealthy? The answer might lie in a catastrophe older than the cluster itself. Just a few light-years away lies the shattered remnant of a hypernova, a stellar explosion so violent it makes regular supernova look like firecrackers. Hypernova occur when especially massive stars collapse, their cores turning directly into black holes while their outer layers detonate with enough force to seed entire star systems with freshly forged metals. If NGC 265 formed from gas enriched by this nearby cataclysm, it would explain the cluster's bizarre chemistry. Picture a cosmic phoenix rising from radioactive ashes, its newborn stars birthed from the debris of a predecessor's apocalyptic end. But the plot thickens when we examine the cluster's structure. Unlike the chaotic sprawl of most young clusters, NGC 265 boasts an almost fractal symmetry, its stars arranged in delicate, branching patterns that evoke a snowflake magnified 1 trillion times. This geometry is no accident. Hypernova shockwaves don't just scatter metals, they compress interstellar gas into intricate, lace-like sheets, creating ideal conditions for stars to form in synchronized geometric bursts. Simulations show that when such shockwaves collide with pre-existing gas clouds, they can trigger cascading star formation along shock fronts, sculpting clusters with unnatural precision. NGC 265's snowflakes might be the frozen imprint of that ancient explosion, a stellar fingerprint pressed into the cosmos. Yet there's an even wilder possibility. What if the hypernova didn't just enrich this cluster but birthed it directly? Some models suggest hypernova can trigger gravitational instabilities so severe they collapse entire molecular clouds in their wake. In this scenario, NGC 265 stars didn't form from pre-enriched gas, they might have condensed directly from the hypernova's own metal-laden ejector, like raindrops crystallizing around particles of dust. That would make them not just witnesses to the explosion, but literal children of the blast, their atomic cores forged in the same fire that doomed their progenitor. The implications ripple far beyond one pretty cluster. If hypernova can seed metal-rich stars in metal-poor galaxies, they might solve a long-standing cosmic mystery: how some dwarf galaxies sport surprisingly modern stellar populations despite their ancient origins. These stellar snowflakes could be proof that even the universe's quietest corners get occasional deliveries of heavy elements, not through slow cosmic evolution, but in sudden, violent gifts from the darkest of celestial furnaces. So is NGC 265 a hypernova's legacy, or something even rarer? Its very existence forces us to reconsider how elements spread through the cosmos, revealing a universe where the line between destruction and creation isn't just blurred, it's woven from the same atomic threads. And as we trace those threads back to their fiery source, we're reminded that sometimes the most beautiful things in space are born from the most unimaginable violence. LHA 115 and 84 isn't your average cosmic cavity, it's a 600 light-year wide superbubble with a twist, literally. this colossal void in the Small Magellanic Cloud looks less like a smooth sphere and more like a soap bubble pinched between cosmic fingers, its edges warped into bizarre, irregular ridges. Most superbubbles form when stellar winds and supernova carve out space, leaving behind clean, rounded shells. So why does this one resemble a crumpled piece of celestial paper? The answer lies in a perfect storm of violence, not one, but multiple generations of stars conspiring to sculpt something far stranger than nature typically allows. Picture the scene, a bustling stellar nursery where massive stars are born, live fast and die young. Each of these giants pumps out fierce stellar winds, particle blasts strong enough to push surrounding gas outward like snowplows clearing a road. When the first generation explodes as supernova, their shockwaves collide with these pre-existing winds, creating a growing cavity. Normally, the process stops there, a single round bubble etched into space. But in La 115 and 84, the story doesn't end. New stars ignite along the bubble's edge, their own winds and eventual supernova adding fresh bursts of energy. Each explosion strikes the cavity's walls at different angles, pummeling the gas from multiple directions like fists shaping clay. Over millennia, this relentless piling on of force crumples the bubble's surface into those surreal, jagged contours. Simulations reveal just how chaotic this process gets. When astronomers model the interactions, they see shockwaves ricocheting off one another, creating turbulence so intense it braids the gas into intricate knots. Some regions get stretched thin, while others pile up into dense ridges, explaining why LHA 115 and 84's shell glows unevenly in X-ray images, with some areas blazing brighter where compression heats the gas to millions of degrees. The most striking detail, the bubble's western flank bows inward sharply, as if punched by an invisible fist. That dent aligns eerily with the current position of a massive star cluster, suggesting its winds are still actively deforming the structure in real time. But the real magic lies in the chemistry. The gas along the bubble's twisted ridges is laced with heavy elements: oxygen, neon, silicon, the forged remains of dead stars. Normally, these metals would disperse evenly. Here, they've been shoved into chaotic pockets by the mess of collisions, creating bizarre chemical hotspots where elements clump like spices in unmixed batter. This uneven distribution could seed future stars with wildly different ingredients, potentially birthing planetary systems unlike anything in our cosmic neighborhood. What makes LHA 115 and 84 truly extraordinary is its defiance of time. Most superbubbles fade as their energy dissipates into the void. This one, it's a living fossil, its wrinkles preserving a record of every explosion, every stellar wind, every collision that shaped it. Peering into its warped shell is like reading tree rings, each ridge a chapter in a saga of cosmic violence stretching back millions of years. And somewhere in that twisted geometry, there might even be clues to a deeper mystery: how dwarf galaxies like the Small Magellanic Cloud, with their fragile gravity and sparse gas, manage to recycle the ashes of their stars into new generations at all. So is it a relic of chaos or a blueprint for rebirth? Perhaps both. Because in this crumpled superbubble, destruction and creation aren't opposites, they're partners in a dance that shapes galaxies one twisted cavity at a time. Among the graveyard of stellar remnants in the Small Magellanic Cloud, one object refuses to die properly: SMC-SNR1, a white dwarf that cheated death in the most spectacular fashion. Dubbed the zombie star, this cosmic survivor did something textbooks say should be impossible. It endured its own supernova explosion, emerging from the firestorm not as a smoldering cinder, but as a still flickering ember clinging stubbornly to existence. Most white dwarfs meet their end in one of two ways: fading quietly into cold darkness or detonating completely as Type I supernova. Stellar bombs so precise, astronomers use them as cosmic measuring tapes. SMC-SNR1 chose a third path, a botched explosion that left it half dead, half alive. When telescopes first studied this object, the evidence was baffling. The surrounding nebula glowed with all the classic signatures of a Type Ia blast: iron, silicon, and nickel scattered across light years, yet at its heart, the white dwarf itself still burned, its surface temperature clocking in at a blistering 50,000 Kelvin. It was like finding a charred fuse leading not to an empty crater, but to a still smoking gun. So how does a star survive its own funeral? The leading theory involves what's called a partial detonation, a supernova that misfires. Normally, when a white dwarf reaches critical mass, usually by siphoning gas from a companion star, the carbon in its core ignites like a stellar powder keg, burning unstoppably until the entire star disintegrates. But in SMC-SNR1's case, the burning might have been lopsided. Imagine lighting a firework with a damp fuse. Some sections explode violently while others fizzle. Here, the detonation could have ripped through just one hemisphere of the white dwarf, blasting it into space while leaving the opposite side relatively intact. The result, a stellar Jekyll and Hyde, half obliterated, half still shuffling forward with enough nuclear fuel to keep shining. But the strangest twist isn't its survival, it's what's happening now. Spectroscopy reveals that SMC-SNR1 isn't just cooling passively like most white dwarf remnants. It's still burning elements in its remaining shell, likely helium siphoned from its companion before the explosion. This makes it a cosmic paradox, a white dwarf technically dead by stellar standards, yet still running on borrowed time like a ghost with a heartbeat. The zombie metaphor isn't just cute, it's eerily accurate. Then there's the companion star, or rather, the lack of one. Traditional Type Ia supernova require a binary partner to feed the white dwarf mass. Yet deep exposures show no sign of a surviving donor star nearby. Was it vaporized in the blast, ejected at high velocity, or was SMC-SNR1's partner another white dwarf, its remains now scattered invisibly in the nebula's glow? The absence raises profound questions. If no companion triggered this explosion, what did? Some theorists speculate that two white dwarfs might have collided directly, a cosmic car crash where one vehicle blew up while the other limped away with severe injuries. What makes this zombie star truly groundbreaking is its implication for cosmic measurements. Type Ia supernova are considered standard candles. Their uniform brightness lets astronomers gauge distances across the universe. But if some white dwarfs can partially explode, leaving behind survivors like SMC-SNR1, our cosmic yardstick might need recalibrating. Suddenly, the universe's expansion rates, dark energy calculations, even the fate of other dead stars come into question. For now, SMC-SNR1 continues its eerie half-life, a celestial warning that even death isn't always final in the cosmos. And as it lingers in its spectral twilight, it forces us to reconsider one of astronomy's oldest assumptions, that when stars go supernova, they leave nothing behind but echoes and dust. Sometimes, against all odds, something remains, and in that stubborn flicker, the universe whispers its most unsettling secrets. Our next anomaly requires us to rethink time itself, a pulsar that spins slower than any other known object of its kind, each rotation stretching across hours instead of milliseconds. But how such sluggish motion defies physics is a riddle written in the silent spaces between its beats. Buried deep within a shroud of cosmic dust so thick not even visible light can escape, Estisage J004854 62,732,253. 9 isn't just a stellar nursery, it's a blackout birth ward where stars form in near-total darkness. This infrared-only enclave in the Small Magellanic Cloud defies conventional observation, its secrets locked away behind an impenetrable curtain of interstellar soot. While most star-forming regions announce their presence with radiant nebulas and glittering young stars, this shadowy pocket operates in stealth mode, its entire population of protostars glowing only in wavelengths our eyes can't see. What makes this nursery so extraordinary is the sheer density of its hiding places. Each fold of dust in this sprawling complex stretching over 30 light-years cradles not just one or two infant stars but entire litters of stellar embryos. Infrared telescopes like Spitzer and JWST have peeled back the veil to reveal hundreds of heat signatures, each representing a sun in its earliest stages of formation. These aren't the bright, boisterous young stars seen in clusters like the Orion Nebula. They're cosmic newborns still swaddled in their dusty amniotic sacs, some so freshly collapsed from gas clouds that nuclear fusion hasn't even ignited in their cores yet. The environment here plays by different rules than stellar nurseries in our Milky Way. The Small Magellanic Cloud's low metal content means its dust grains lack the heavier elements that help gas clouds cool efficiently, a critical step for star formation. Yet against all odds, Enigma J04854, 62,732,253, is a production line for new stars, churning them out at rates that rival richer galactic neighborhoods. The secret might lie in the dust itself. Spectroscopy reveals these obscuring clouds aren't made of the typical silicon-based grains, but carbon-rich molecules that clump together in fractal patterns, creating an ultra-fine cosmic mesh. Think of the difference between beach sand and powdered graphite, one coarse and granular, the other capable of forming dense, velvet-like sheets. This unique structure could allow the cloud to fragment more easily, bypassing the need for efficient cooling by sheer gravitational persistence. Then there's the nursery's bizarre thermal signature. Most star-forming regions display a mix of temperatures: hot young stars, warm gas, and cold dust all coexisting. Here, everything registers in the same narrow band between -250 and -200 degrees Celsius, a deep freeze where even molecules move sluggishly. The only exception, pinprick hotspots around each protostar, where gravitational collapse heats tiny cores to a few thousand degrees. It creates a surreal thermal map, an icy black sheet studded with faint, evenly spaced embers, like a circuit board viewed through liquid nitrogen fog. But the real jaw-dropper comes when we examine the star's arrangement. Instead of random scattering, the protostars align along filamentary structures, invisible magnetic highways winding through the dust. These filaments aren't straight lines but twisted helices, as if the entire cloud is a colossal DNA strand with stars for nucleotides. Some theorists believe this could be evidence of large-scale magnetic fields braiding the gas as it collapses, imprinting order onto chaos. Others suggest it's the fossil imprint of a galactic collision millions of years ago, with shock waves from the impact sculpting the dust into these eerie, spiraling tendrils. What emerges from this darkness won't look like the stars we know. The Small Magellanic Cloud's chemical poverty means these newborns will mature into stars with radically thin atmospheres, hot, blue, and burning fiercely with fewer metals to block their radiation. Some might even lack the materials to form rocky planets, their planetary systems dominated by gas giants or ice worlds. Yet for all their strangeness, these shadow-cradled stars represent something universal: the persistence of creation, even in the universe's most unlikely corners. So is Enigma J04854, 62,732,253. A cosmic anomaly, or a glimpse into how the first stars formed in the early universe's metal-free voids, perhaps both. Because sometimes the most illuminating discoveries aren't found in the light but in the perfect darkness just beyond its reach. Swirling through the Small Magellanic Cloud like a tempest frozen in time, DML 299 isn't just a nebula, it's a cosmic tornado, a vortex of gas and dust spinning on an axis so precise it completes a full rotation only once every 1,000 years. Stretching nearly 20 light-years from base to tip, this spiraling behemoth moves with an eerie, deliberate grace, its glowing tendrils tracing perfect helices against the void. Most interstellar structures tumble chaotically or dissipate quickly, but DML 299 maintains its coiled structure with unnatural persistence, as if some unseen force holds it in place like a celestial spindle. The mystery isn't just its shape, it's the energy source keeping this whirlwind alive. Nebulae this large typically dissipate within millennia, their gases scattering under pressure from stellar winds or radiation. DML 299, however, has churned for at least 50,000 years, its structure growing more defined with time rather than fading, the leading suspect. A runaway neutron star, invisible to telescopes but betrayed by the wreckage it leaves behind. Picture this, a hyper-dense stellar corpse, no larger than a city but weighing more than our sun, rockets through interstellar space at breakneck speed. As it plows through gas clouds, its immense gravity and magnetic field twist the surrounding material into a spiraling wake, like a speedboat carving curls into water. But here's where the plot thickens. DML 299's rotation period, that stately 1,000-year turn, doesn't match the frantic pace expected from a typical runaway neutron star. Most leave behind turbulent, short-lived trails as they zip through space at thousands of kilometers per second. This vortex rotates slowly, almost regally, suggesting its engine might be something even stranger. A magnetar, a neutron star with a magnetic field so strong it warps spacetime itself. Such an object wouldn't need to move quickly to sculpt its surroundings. Its field alone could stir gas into these colossal, languid spirals, like a spoon gently swirling cream in coffee. Then there's the chemistry. DML 299's outer layers shimmer with ionized oxygen and neon, elements typically forged in supernova and carried outward by shock waves. Yet instead of dispersing evenly, these metals are concentrated along the tornado's walls, threaded through the glowing filaments like veins in marble. This peculiar distribution hints that the original explosion wasn't a symmetrical blast, but a lopsided detonation that launched debris in a focused jet, exactly the kind of violence expected when a magnetar is born. Yet for all these clues, the tornado's heart remains hidden. No pulsating X-ray source or radio beacon marks the neutron star's position. It may have moved on, leaving its whirlwind to spin autonomously like a ghostly top, or it could be shrouded by the very gas it's stirring, its emissions absorbed before they reach us. Alternatively, DML 299 might not owe its structure to a neutron star at all. Some theorists propose it's the product of colliding magnetic fields, a cosmic-scale version of the vortices that form when opposing currents meet in Earth's oceans. The Small Magellanic Cloud's turbulent history includes multiple galactic collisions, any of which could have tangled magnetic field lines into knots capable of shaping gas into this eerie helix. What makes DML 299 truly mesmerizing is its defiance of scale. Tornadoes on Earth last minutes and span miles. This one has raged for millennia across light years, a storm so vast its winds shape the birthplaces of future stars. Embedded within its whirling arms are dense knots of gas stellar embryos cradled in the vortex's curves, their fate tied to the tornado's slow, inevitable unwind. Will they be flung free when the structure finally dissipates or swallowed by whatever engine still lurks at its core? For now, the cosmic tornado keeps spinning, its secrets locked in the deliberate turn of its ancient dance. And as we watch, we're reminded that sometimes the universe's most enduring mysteries aren't found in the explosions or the collisions, but in the quiet, persistent motions that outlast them all. Tucked away in the outskirts of the Small Magellanic Cloud, a shadowy structure lurks, one that might rewrite the history of this dwarf galaxy. Designated SMAC Nod, this faint collection of ancient stars doesn't behave like anything else in the vicinity. It's not quite a globular cluster, not quite a galaxy, but something in between, a cosmic chimera that astronomers are calling the missing link. What makes SMAC Nod so extraordinary isn't just its odd shape or dim glow, but what it represents, a living fossil from the early universe, possibly one of the original building blocks that helped construct the Small Magellanic Cloud as we know it today. Most galaxies grow like cosmic patchwork quilts, stitched together over billions of years from smaller star clusters and dwarf galaxies. Smag Nod fits the profile of one of those primordial pieces, a relic so old. Its stars contain almost no heavy elements, a telltale sign they formed when the universe itself was still in its infancy. But here's the twist. Unlike other surviving building blocks, which usually orbit their host galaxy like bees around a hive, Smag Nod is embedded deep within the Small Magellanic Cloud's outer halo, as if it's being slowly digested. That raises a tantalizing question. Is this the last untouched remnant of the galaxy's assembly, or the half-chewed remains of a meal from long ago? The evidence cuts both ways. On one hand, Smag Nod stars move in near-perfect sync with the Small Magellanic Cloud's rotation, suggesting they've been part of the system for eons. On the other, its elongated shape, stretched like taffy, hints at gravitational disruption, the kind that happens when a smaller galaxy gets torn apart by a larger one. The smoking gun might lie in its chemical fingerprints. While most of the Small Magellanic Cloud stars show traces of heavier elements forged in later generations, Smag Nod's stellar population is pristine, untouched by the pollution of supernova. That purity suggests it formed in isolation, only to be captured later, like a cosmic time capsule waiting to be opened. Then there's the location. Smag Nod sits at the exact boundary where the Small Magellanic Cloud's gravity begins to lose its grip, a no-man's land where stray stars and rogue clusters often wander. This precarious position makes it a celestial Rosetta Stone. Study it, and we might finally decode how dwarf galaxies like this one evolve. If Smag Nod is a surviving building block, it could reveal the original recipe for galaxy formation. If it's cannibalized debris, its stretched-out stars could map the Small Magellanic Cloud's gravitational field like breadcrumbs leading back to a long-forgotten feast. But the most intriguing possibility, Smag Nod might be both a builder and a meal. Some simulations suggest that the smallest galaxies didn't just merge smoothly. They engaged in a sort of cosmic cannibalism where larger fragments consumed smaller ones while still in the process of assembling. In this scenario, Smag Nod could be a half-digested remnant of that chaotic era, a snapshot frozen mid-bite. Its very existence blurs the line between construction and destruction, reminding us that in the cosmos, creation often wears the mask of violence. For now, the mystery lingers. Each new observation peels back another layer, revealing subtle clues. A slight warp in the star distribution here, an unexpected metal ratio there. But answers are tantalizingly close. Upcoming telescopes like the Vera Rubin Observatory could finally settle the debate, measuring Smag Nod motions with enough precision to trace its orbital history like a celestial genealogy. Until then, it remains a ghost at the feast, a silent witness to the Small Magellanic Cloud's tumultuous past, and perhaps a key to understanding how all galaxies find their place in the universe. And as we stand on the brink of discovery, we're reminded that sometimes the most profound truths don't come from the brightest objects, but from the faintest whispers of starlight echoes of a time when galaxies were just learning how to shine. At the far edge of the Small Magellanic Cloud, a planetary rebel defies every rule of cosmic construction. SMC Exo 7b, a Neptune-sized world that shouldn't exist. This bloated gas giant circles a star so metal-poor, astronomers initially dismissed the possibility of finding planets there at all. The host star, catalogued as SMC MP44, contains just 8% of the iron and silicate found in our Sun, a composition typical of the Small Magellanic Cloud's primordial stellar population. Yet against all odds, this cosmic underdog has managed to forge a planetary companion 10 times heavier than Earth, orbiting closer than Mercury does to our Sun. How does a planet form in such a hostile environment? The standard model of planetary birth faces a crisis here. In metal-rich systems like ours, dust grains clump together easily, their icy coating sticking like cosmic Velcro to build planetary cores. But SMC MP44 protoplanetary disk would have been virtually dust-free, more like a thin soup of hydrogen and helium with barely any solid particles to seed planet formation. That scarcity should have left the system barren, yet SMC EXO 7b stands as living proof that nature improvises. One radical theory suggests this planet might be a refugee, born elsewhere and later captured by its current star. The Small Magellanic Cloud's chaotic gravitational environment could have flung a rogue planet into SMC MP44 grasp, where tidal forces then circularized its orbit. But there's a problem. SMC EXO 7b's atmosphere shows chemical signatures matching its star's peculiar composition, implying it formed locally rather than arriving from foreign skies. Another possibility turns planetary formation theories upside down: gravitational instability. In this scenario, swirling eddies in the protoplanetary disk could have collapsed directly into a gas giant, bypassing the need for a solid core entirely. Normally, this process requires frigid temperatures far from the host star, yet SMC EXO 7b orbits blisteringly close. The solution: the planet might have spiraled inward after forming farther out, dragged by interactions with residual gas in the disk, though why it stopped where it did remains a mystery. The most tantalizing clue comes from the planet's bloated radius. Despite its mass, SMC EXO 7b is 20% larger than Neptune, its atmosphere puffed up like a cosmic souffle. This could point to extreme internal heating, possibly from tidal forces or residual radioactivity, but it might also hint at an exotic composition. With fewer heavy elements available, the planet could be predominantly hydrogen and helium, structured in ways that defy our solar system's chemistry. As we close our tour of the Small Magellanic Cloud's strangest objects, SMC EXO 7b stands as a fitting finale, a cosmic paradox that challenges our most fundamental assumptions. Its existence whispers a provocative truth: that planets can form in environments we once deemed impossible, under rules we're only beginning to decipher. And if that's true here in this quiet dwarf galaxy, what other planetary marvels might be waiting in the universe's uncharted corners? The answer could rewrite not just how we understand planet formation, but where we should look for other worlds and perhaps other life among the stars. Amid the Small Magellanic Cloud's tapestry of cosmic oddities, one anomaly stands apart, not for what it emits, but for what it swallows. Object 13 doesn't glow, doesn't pulse, doesn't even cast a shadow. It's a gravitational phantom, a patch of space where stars move as if tugged by something colossal, yet telescopes reveal nothing. For decades, this invisible knot of mass defied explanation, dismissed as a statistical fluke or calibration error. But new research suggests we've been staring at something extraordinary, a mini-halo of pristine dark matter, untouched since the dawn of time. Unlike the diffuse dark matter that permeates galaxies, mini-halos are theorized to be dense clumps of primordial particles, relics from the universe's first microseconds, when quantum fluctuations froze into physical form. Most should have evaporated or merged long ago, but a rare few might survive in galactic backwaters like the Small Magellanic Cloud, where gravitational chaos hasn't shredded them. Object 13 fits this profile perfectly. Its gravity signature, measured by the way it bends starlight and distorts stellar orbits, points to a compact sphere of mass roughly 30,000 times heavier than our Sun, packed into a space no wider than our solar system. That density rules out conventional explanations like rogue black holes or neutron star clusters. The smoking gun microlensing surveys: when unseen masses pass in front of background stars, they magnify their light briefly like a cosmic magnifying glass. Most lensing events last days or weeks, but Object 13's distortions persist for months, suggesting an extended structure rather than a pinpoint mass. Even stranger, the lensed stars don't brighten symmetrically. Some flicker erratically, as if the lens itself has a lumpy texture, exactly what simulations predict for a mini-halo's granular dark matter. Then there's the motion. Stars skirting Object 13's edge accelerate suddenly, their trajectories kinked as if brushing against an invisible current. This matches models of dark matter streams, filaments of particles flowing through mini-halos like wind through a sieve. If confirmed, these streams could reveal the dark matter's temperature. Cold dark matter, slow-moving particles, would leave smooth stellar deviations, while warmer varieties would create jagged jumps. Early data leans cold, supporting theories that the earliest dark matter formed heavy, sluggish particles. But the most tantalizing clue comes from the Small Magellanic Cloud's own history. Dwarf galaxies like this one are thought to be dark matter crucibles, their shallow gravity wells preserving ancient structures that larger galaxies shred. Object 13's position near the galaxy's outer fringe, far from disruptive stellar nurseries or black hole mergers, makes it an ideal time capsule. Its sheer isolation suggests it survived undisturbed for billions of years, a frozen fragment of the universe's first dark architecture. What could this mean for cosmology? If Object 13 is a mini-halo, it's proof that dark matter isn't just a featureless fog, but has texture, clumps, and streams that could seed galaxy formation. Its existence would validate exotic theories like action dark matter, where ultralight particles condense into cosmic puddles, or it might hint at something wilder, a shadow universe of dark atoms and molecules hidden in plain sight. For now, the phantom's true nature remains veiled, but with new instruments like the Vera Rubin Observatory coming online, we may soon peer deeper into this gravitational riddle, and in doing so, glimpse the universe's oldest, darkest blueprint. Because sometimes the most profound truths don't shine, they pull. Peering into the depths of the Small Magellanic Cloud isn't just about powerful telescopes, it's about human ingenuity bending light, time, and even physics itself to unravel these cosmic riddles. Take the Hubble Space Telescope, for instance, whose razor-sharp vision has captured the ghostly filaments of supernova remnants like E0102 in stunning detail. But Hubble doesn't work alone. On the ground, the Atacama Large Millimeter Array ALMA acts as a cosmic ear, tuning into the faint whispers of cold gas and dust that optical telescopes miss. Together, they're like a detective duo. Hubble snaps the crime scene photos while ALMA dusts for fingerprints, yet some mysteries demand even stranger tools. To map the invisible tug of dark matter around Object 13, astronomers turn to gravitational lensing, a trick where distant stars act like backlit candles. When their light bends around unseen mass, it reveals the shape of the phantom, no different than tracing a silhouette by its shadow. Meanwhile, X-ray observatories like Chandra dissect the high-energy tantrums of objects like SMCX-3, capturing eruptions hotter than a million suns. Each wavelength of light peels back another layer of the story, from infrared's view of stellar nurseries shrouded in dust to radio telescopes eavesdropping on the magnetic screams of neutron stars. But the real magic happens when data meets creativity. Take the zombie star SMCSNR1. Its survival was only confirmed when astronomers compared decades-old photographic plates with modern digital scans, spotting the white dwarf's faint glow persisting like a timestamp across the ages. Similarly, the rhythmic bursts of SMCFRB1 weren't solved by a single observation. It took a global network of radio dishes from Australia to Chile, working in unison to catch every pulse and piece together its celestial metronome. And then there are the unsung heroes, supercomputers that simulate cosmic violence frame by frame. Before we understood the twisted superbubble LHA 115 and 84, researchers spent months running simulations of colliding stellar winds, watching digital gas clouds crumple into identical jagged shapes. It's a reminder that behind every eureka moment are countless hours of trial, error, and coffee, because sometimes you have to break the universe in a computer before you can understand it in the sky. The human element is just as crucial. When ALMA detected the crystalline hydrocarbons painting DML 203's geometric glow, it was a team of organic chemists, not just astronomers, who decoded the infrared signatures. Citizen scientists have scoured telescope data for anomalies, their fresh eyes spotting patterns algorithms missed. Even the language we use reflects this collaboration. Terms like blue stragglers or cosmic string aren't cold scientific labels, they're stories condensed into phrases, crafted to capture imaginations as much as phenomena. So the next time you see an otherworldly image from the Small Magellanic Cloud, remember, it's not just a snapshot. It's a mosaic of human curiosity, built from midnight observations, heated debates, and the quiet thrill of seeing something no one has seen before. Because in the end, these aren't just telescopes and algorithms exploring the cosmos, it's us. From diamond-studded white dwarfs to cannibalistic black holes, the Small Magellanic Cloud isn't just a collection of cosmic oddities, it's a revolutionary laboratory where the universe tests its wildest ideas. These 30 objects don't merely defy expectations, they rewrite the rules of astrophysics entirely. Take the zombie star, surviving its own supernova like a phoenix rising from radioactive ashes, or the ghostly empty bubble, a supernova remnant scooped clean by forces we can't yet name. Each discovery peels back another layer of our assumptions, revealing that dwarf galaxies aren't just smaller versions of their spiral cousins. They're anarchic playgrounds where chemistry, magnetism, and gravity conspire in ways we've never seen. Consider the implications. A rogue planet like Ogle SMC1 suggests worlds might form freely in the void, unshackled from stars. The Thorn-Zitkow object HV2112 hints that stellar hybridization could be more common than we imagined. Even the seemingly humble SMC bar barrier, an invisible magnetic fence corralling star formation, challenges how we model galactic evolution. Together, they paint a portrait of the Small Magellanic Cloud not as a cosmic backwater, but as a vibrant frontier where the universe's strangest experiments thrive. What makes these findings so thrilling isn't just their individuality, but their collective message: dwarf galaxies are anything but simple. Their low metal content, turbulent histories, and weak gravity don't stifle complexity, they breed it. From crystallized carbon nebulae to pulsars that spin faster with time, the Small Magellanic Cloud proves that when the universe strips down its ingredients, the results aren't duller, they're dazzlingly unpredictable. So which of these cosmic rebels resonates with you? Is it the ticking time bomb of SMC X3 or the mirrored elegance of the twin planetary nebulae? Dive into the comments and share your favorite, because the best part of discovery isn't just finding answers, but sparking the conversations that lead to the next great revelation. After all, the universe's weirdest wonders are best explored